So in this module, we're going to look at steel and do a little bit of calculating. So I wanted to give a brief overview of some issues about steel that I hope you'll find interesting. We're going to do kind of a deeper dive into this idea of AESS, which is architecturally exposed structural steel. The real distinction there is that the idea is qualifying it so that it is understood by all parties in the process that it's going to be visible and the qualities that need to go along with that. And so here's a great example of exposed steel. A lot going on, curved beams, adaptive truss systems, this nice mix of wood with it, but fancy but not over the top, I guess, as far as extreme goes. One of the things we're going to do with this project is we're going to look at this project here, which is in Chicago. It's an expansion to the Modern Art Gallery, and which one it is escaping me right now. Renzo Piano. This project, and it has this nice secondary roof system or overstructure, and I thought this would be a great way to deal with this idea of exposed structural steel and the structural calculations that go along with it. And it's a pretty popular method of construction nowadays. So here we have, I think this is like a Google headquarters building. This is an outdoor area with the same kind of metal structural system overhead. It looks like steel with wooden secondary members to it. And here it is, very similar. This is now a McDonald's. I believe this is in Chicago. I'm not sure if these are hyperlinked. Yes, this one is hyperlinked. This is their flagship in Chicago. You can go ahead and visit with that link. And it's really an over-the-top McDonald's. It's very high-end looking. But I'm drawing that connection because here now they're using solar collectors in this superstructure of exposed steel. Another thing we'll always be presented with as architects is one of the great advantages of steel is the ability to really do kind of amazing visual feats. And one of them is cantilevers. So here we have a couple of cantilever projects. Typically what identifies structural systems, just to make you familiar with them, is at some place there's usually an embedded truss system. And here we have the truss with its diagonal units to brace it, to create the truss function. And it gives you a little idea of the structural feat that's going on in order to create this cantilever. And here's probably one of the most extreme ones I've ever seen. Structural steel cantilever. It's the largest of its kind according to its statement in the U.S. And here they're using a really clever way of kind of disguising the structural system. So if you look up in this view, you'll notice it looks like there's no structure other than the parapet and the spandrel area, I guess if that's what you'd consider it in a single-story building, creating this really immensely long span. But if you dig deeper and you look at the structural underlying form here, you'll notice that these trusses have been pushed back within the building. And you can see them, and they now become elements right inside of the building, but we still have these immense truss systems, these beautiful bolted connections inside the office environment. And probably carefully arranged in order to, but still obstructing kind of the flow of the interior space. But that was an acceptable trade-off in this project in order to deliver this kind of lightweight looking cantilevered structure. So keep that in mind if you're doing cantilevers, this idea of the truss-like structure that needs to support it. In this case, these bolted connections as opposed to welded connections, and this really becomes another element as in the interior of the building. A few steel basics. I'll cover these if you haven't had them before in other classes. Typically, when we're talking about architectural steel, we're talking about W sections, wide flange sections, as opposed to what we typically call this is an I-beam, and an I-beam has this kind of a formed section to it, an S section typically. So when we talk about the steel that we're usually using in architecture, we're usually referring it as W sections, wide flange beams. and I've got the nomenclature here. One of the things to take note, and I don't know if I have this in another, um, the typical two defining terms of the beam are its height, how deep it is. So it would be a W, let's say a 12 by X. I mean, X might be 15 or 20 or 75, and that second designation, that 12 by whatever, is the pounds per foot. And maybe I'll try to clarify that in some other slides here. Another thing to keep in mind as architects is that we have some control over what these things look like, especially if we're concerned about their appearance. We can build up sections of steel. In this case, we have an I-beam attached to a piece of shoring. But here's all kinds of composed welded sections. So two C channels together, face to face to make something that looks tubular, back to back to make something that looks like an I-beam. The combinations of I-beams, of L sections. There's a whole bunch of ways that you can build up these elements in order to create both the structural properties and the appearance properties that you would desire. Connections, a big part of our discussion when we're doing steel work, and typically our connections are considered shear connections. We don't transfer moments between them unless they are acting to perform as a moment frame for shear performance within the building. So here we have the first image is just a bolted connection, and you'll notice that there is this kind of clearance that's around the flanges in order to make sure that we're not transferring any moment from deflection of this beam into our column system. Now, in order to change this from a moment frame, or excuse me, from a shear connection, a bolted connection, to a moment frame, in this case it's welded, so that the attachment at all points is welded. It would be anticipated that this I-beam could actually just be cantilevering out. In this case, that would never be the condition for this type of a bolted connection. So we're not trying to transfer any kind of moment forces through these connections, and and our strongest intention is to be able to deliver moments through these. One of the current trends is heavy timber construction, and it has advantages because of its fire resistance, and I think it's a good time to compare and contrast this idea of fire resistance and the kind of fragility of steel to high temperatures. So here we have just some graphic views of what happens to steel when it's exposed to intense heat, the kind of deflections and deformations within the flanges, and some of the treatments to prevent that issue, fire issues within the structure that would deteriorate the structural performance, and that are insulation over the metal in order as a form of fireproofing to delay the effects of heat. We have painting systems, intumescent systems that actually look smooth until they are exposed to heat, and then they create a kind of a foamed surface that increases the kind of thermal resistance and works to protect the beam. There are other ways to protect our beams, and one of the easiest ones is to encase them in gypsum board. And so this is just a good graphic of how you would build up gypsum board around an I-beam in order to protect it from damage from heat from a fire. And obviously that's kind of counter to what you might intend if you wanted to expose your structural steel. And so one of the ways to address that, if you're going to have exposed steel and you want it and you're concerned about its appearance, it's more than likely that your protection for the structure, for the steel, would be a sprinkler system. So here we have a good illustration of exposed steel. In this case, it's probably not an appearance grade. This could just be a factory floor, but in any case, it is protected. It protects the structure and the occupants with these red lines, which are the plumbing for the sprinkler system. This is a link that's available to you. This takes you to the preparation for the architectural, the AREs, exams and about structural systems, because I think this is a good point to kind of like make you aware of what things licensing requires for you to understand about structural members and elements. And it's just a good chance for you to review if you want to click through to this, and it'll actually take you to a link where you can actually do a practice test. So as I was kind of leading into this idea of architecturally exposed structural steel, one of the features of the project we're working on, but also probably one of the places where we want to focus as architects, mostly in understanding the structure and the requirements of appearance. So here we have just a nice starting image. We have all exposed structural systems, all painted, a roof decking, a column system. I don't exactly know why this is quite so complicated as it is, whether it's just maybe possibly just mostly for decorative reasons or to reduce some of the number of columns. But it's quite a challenge to deliver this load from out to these points to this column load. But you can see this, one of the nice things about this is these are actually tapering, and you can see where the maximum moment or loads on these members, because they're working as lever arms, is where they make attachment to the column. So they actually thicken up at that point. So here we have some more, I think, really beautiful examples of exposed structural steel. We have a wooden deck with its cross members and that wood exposed, but the underlying space frame kind of techniques that we've used in our creation of form being used to generate our patterns for our steel gridded system. The unique features here, you can notice how all of these members in the interior of the frame are about the same depth. But as we get to the edge condition where there's no extra load coming from another member, these are actually tapering down. And then this final exterior element is of less depth than the interior ones are. And then we have interior columns. This is a very typical articulation of beautiful structural interior columns, more for show than for structure. And I kind of want to start to make you sensitive to this idea that the connections are of visual interest. They add value to the interiors of our buildings by that interest, by that kind of revealing of structure. And that's funny, that one's appearing again, but as a healthy reminder that if these are exposed and we don't have fireproofing, there is a method of actually applying a paint that will be fire protective. And just another few examples of exposed structural steel. Once again, I find the bolted connections are obviously very nice. These would probably be very difficult because these are actually riveted. This is probably an older structure, so we're not seeing bolts here, but we're actually seeing rivets. But here's another just beautiful roof systems being carried down to other load members. Wild framing. Another beautiful example of a column system and a roof system, and transparency of it. Looks like this is probably an infill system around a historic building. And then just for your own kind of, I guess, sensitivity to the idea of how you specify and what's required of it. On the left here we have a beam that's been probably plasma cut or maybe flame cut. And you'll notice this kind of spatter that comes off of the cutting of the torch. All beams don't have to be cut this way, but depending on the fabricator, all of this would need to be removed. And this is actually, if you look at this 57A17, so here it is in its first cut form, and then here it is cleaned up and painted. And you can see the things that are actually removed. The weld spatter has been removed. The markings still exist. That would be probably commonly understood in our grading of this as an exposed piece of steel. You can also see pock marks in the face of that from the rolling operation of forming it. That's typically normal. and you'd probably be considered over the top to expect smoothness in that level of performance. So here again, I'm pointing up this grade symbol on the steel. It may be required, it may not be. I see something really nice here. These bolts, these are graded bolts, but you'll notice they don't have a head on this end. They don't have a hex. They actually look riveted. And on the inside, the bolting is so you could have connection systems that really look more like they're riveted because they're disguising the bolting on the inside. So here's would be a typical project, a concourse between two buildings. You want to expose structural steel. You've decided on a pattern system of Xing these together. You've also created kind of a huge difficulty in that you'll have one continuous member and two members that have to intersect to that. And if you look at this illustration, you can see where these welding activities have happened here, and then the typical kind of finishing of that. And this is probably considered a very acceptable quality connection. But you've introduced this idea of a lot of welding and finishing work that has to happen where these two intersect with each other. If these had just been diagonal members, all of this work would have been eliminated and to the, I guess maybe to the loss of the appearance, but it's always a trade-off. This is a nice graphic of the idea of appearance grades. The furthest from you, the lowest grading of quality of the metal as far as finish goes. And as it comes closer to proximity to your eyes and to where you can step up to, you get a higher grade. And I'm pointing out this red one here because this is kind of a disappointment. To me, this is a visual disappointment in the whole thing. This is ductwork that may have not been anticipated in the first part of this. But here we have these beautiful sweeping curved surfaces going along here that were formed. And then the HVAC contractor came in and could only do straight runs of conduit. And so we kind of lose that beautiful flowing feeling within it. I don't know if there's a way to resolve that, but the nice thing about modeling things out is to be anticipatory of those kind of issues. And here's a statement of all of the standards for the quality at the highest, the showcase to a basic quality of exposed structural steel, and then kind of the idea of what is expected and what would be specified in its appearance. I put this one in just because it's amazing. It makes me wonder how they ever got this on site where it was actually fabricated. I can't imagine a truck being able to move this to the site. So there must have been some way to bring these elements in parts and then assemble them on site. But some kind of consideration. How do you if you specify something that has to be factory painted and/or welded, can you transport it to the site? Or where will it be painted? How will the finish be applied? All kinds of technical issues to come up with high quality product. Another piece of exposed steel system, really beautiful. We've done enough now with, I think, module 4 that we can kind of understand how to create these kind of beautiful surfaces. And a reminder about the beauty in the details and not the devil in the details, so as opposed to it. A beautiful connection of elements coming together, very engineering, but still very visually interesting and very descriptive of how that forces are being handled. So here we have these column loads coming in, and we're trying not to generate any kind of moment forces because we've pinned the connection together. And because we're willing to kind of like jump into that world of customizing our steel, we can have a lot of and even more mundane projects and influence about, like in the case of the bow truss here, the curvature of the top and bottom chord. One is is done for drainage. Another one is designed maybe for clearance and or appearance. I have some additional slides available in a PDF form, but is one of the parts to review is this idea of life cycle assessment and the idea of comparing like steel to wood. And I think steel and concrete are both going to be under increased scrutiny nowadays because of this idea of wood being a great alternative in construction, even in high-rise construction, heavy timber. But there are things to consider about the value of steel, um, and I'm only kind of introducing this. That steel lasts a long time. It's very recyclable. It has high performance characteristics. A lot can be done with it in the field, and even in many ways more than can be done with timber as far as misalignment, corrections of field problems, because we can weld steel together and then transfer loads very effectively. If we have a piece of timber that's too short, we can't weld extra wood onto it. But a nice visual here, the kind of factory done pre-build-up of components and then how they fall together as complete systems. I'm not sure we have a video here. I thought this might be hyperlinked. I just wanted you to get a feeling for how these forms are made. So this is a rolling mill. So hot ingots come through, and they get rolled out through dies in order to create the flange depth and the flange height for us. And this is a look through a factory. So on both sides of this, we're seeing a rolling mill, and the product is coming off of this rolling mill and being straightened out. It looks like they have spray to quench this, to cool it down as it's moving through the process. And over here we have all of the dies that are used to create all of the different shapes of I sections, C sections, or whatever in a steel mill. I thought it'd just be interesting for you to have a feeling for how these parts are created. And here we have custom fabricated pieces of steel beam, where we have these gray pieces transverse here are building construction fixtures. So they're flame cutting maybe shapes, roll forming bends, and then a welder comes in and welds this up to be a complete structural section for a building. And I guess that completes kind of our first overview of architecturally exposed structural steel.